Geeta ma'am, good evening ma'am.
Sir, good evening, sir. Madhukumar, sir.
Yes ma'am, hope I am audible ma'am.
Yes, sir. Yes, sir.
Okay.
I'm
Ma'am,
audible.
I made you co-host ma'am.
Yes, sir. Yes, sir.
If I need to do somebody else, you just tell me ma'am.
Madam, sir, if HOD is coming, HOD, sir, Anita, madam, sir.
Yes ma'am, we are live and I will share the brochure meanwhile.
Yes, sir.
Okay, you got YouTube link with your own. Okay ma'am.
Yes, I have sent to all the participants just now.
Yes ma'am. Yes ma'am. I'm sharing the brochure. Okay.
Sure, sir.
ఈడ్చుకొని పడుతుంటే నీ అమ్మ.
Good evening, ma'am.
Sir, good evening, sir.
Ma'am, it's 6.
Yes, ma'am. Yes, sir. Just now, Anita madam called. She will be logging in, sir. Let us wait and let us start after her.
Yeah, yes, ma'am. Yes, ma'am. All the participants are requested to mute yourself. Please follow the webinars Hygiene, just raise your hand in case if you want to interact. Else, stay yourself muted.
Good evening, sir. Good evening, ma'am.
Good evening, sir. Ma'am, good evening, ma'am. Anita, ma'am, good evening, ma'am.
Good evening, Geeta ma'am.
Yes, I'm audible, ma'am.
Yeah, you are audible.
Thank you, ma'am. ஏங்க எடுக்காதீங்க.
Geeta ma'am,
Yes, ma'am.
HOD sir not logged in, no?
Yes, ma'am. He didn't come, seems.
Okay. Just,
Shall I make call?
yeah. You just call him and
Ah.
ask to join, ma'am.
ఏంది మాట్లాడు మళ్ళీ ఆయన తీసుకొస్తాను కదా
Madhu, sir.
Ma'am, good evening, ma'am.
Sir, what shall we do, sir?
We can start, ma'am.
Start, huh?
I made Anita, ma'am, as well as you as co-host, ma'am.
Sorry. Okay. Ma'am, Anita, ma'am, shall we start, ma'am?
Yes, ma'am.
Um,
Yes, ma'am.
A warm good evening to one and all. It is one of the great day for us. We are all going to hear an inspiring talk from a legend from NASA. Yes, today we are having a gather to have an international webinar on printed and flexible electronics by Dr. M. Mayappan from NASA, California. For this memorable event, on behalf of our institution and department, I welcome you all. I would like to invite our ma'am, Dr. B.R. Anita ma'am. She's professor of our department. Welcome, ma'am. And I would like to invite Mr. P. Madhukumar, sir, who is hosting this event. Welcome, sir. And I welcome all the participants for the event. We are all working for Sri Vidyaniketan Engineering College. At this juncture, I would like to uh, call upon our Anita ma'am to give some words on our institution as well as our department. She'll be giving an overview of the title also. Please, ma'am.
Thank you, Geeta ma'am. A warm welcome to one and all to the today's uh, webinar on printed and flexible electronics, and why we have chosen this printed and flexible electronics, and why we invited Dr. M. Mayappan from NASA. So here I would like to say a few words about uh, why we have chosen uh, this printed and flexible electronics, because our institution, that is Sri Vidyaniketan Engineering College, uh, is having a national MEMS design center, and which was inaugurated on 30th March 2012 by Dr. V. Ramgopal Rao Garu. So, who is a former professor in IIT Bombay, and at present he is the director for IIT Delhi. And Dr. S. Mohan, IISc Bangalore, for the benefit of users from this region. So here, with the help of them, we inaugurated this center, and we made this center as a national MEMS design center by equipping with site licenses of softwares, that means software programs such as Coventor, MEMS Plus, IntelliSuite, and COMSOL. So under this national program on micro and smart systems, that is NPMAS. And what is the main motto of this center means, this center is going to motivate the research activities in the field of MEMS by proper utilization of the facilities provided by NPMAS, from design to fabrication of prototype MEMS products and specific field applications. And also, Sri Vidyaniketan facilitate external researchers from other interested institutes, either academic or national labs, subject to individual software licensing conditions, to use the design tools. So in this center, all the departments share the simulation facility supported by NPMAS, and the departments are required to promote the area of MEMS through independent department course at UG or PG levels to involve students and faculties in developing MEMS related projects and research activities. So in the absence of required in-house comprehensive facilities for complete fabrication of MEMS, the short-term strategy is to focus on design, modeling, and characterization with the help of IIT Bombay or IISc Bangalore. So in this direction, in our institution, many of the faculty members were chosen the specialized topics in their discipline and their work is under progress. So even in the institution, we will organize training programs like this on MEMS design using COMSOL multiphysics and MEMS design using Coventerware. And many faculty attended various programs like conferences, workshops, training programs, not only in India, even in international. So this is under this, the center is carrying up many projects which was funded by government of India as well as INUP program and also SVET. So many papers were published in reputed journals and attended national and international conferences, and we have interaction, we have collaboration with many industries and many academic institutions, many research centers. So this is the brief introduction about the National MEMS Design Center in Sri Vidyaniketan Engineering College. So this is the reason why we have chosen this printed and flexible electronics by Dr. M. Mayappan Garu. So thank you, sir, for accepting our invitation and delivering a lecture on printed and flexible electronics. So before going to start actual program, so here I'm going to share the few words. That means share some information about printed and flexible electronics. So here I'm sharing my PPT. Madhu sir?
Yes, ma'am.
Sir, if I am going to share the PPT, this screen is going to disappear, sir.
Yes, ma'am. Yes, ma'am.
Okay.
Yes, ma'am. We can see your presentation, ma'am.
Okay, sir.
Ma'am, 1 second. All the participants are requested to turn off their video.
Sir, is it okay?
Yes, ma'am. It's fine, ma'am.
Okay. Thank you. Okay. So just I'm going to give overview on printed and flexible electronics technology. So what for we have chosen this topic and how it is leading nowadays, how it is leading in the world, not only in the country, in the whole world, it is leading. That means printed and flexible electronics. So if you look at this, that means first, what is the basic introduction of this? Means here, if you consider flexible electronics is a new trend in electronics industry to handle the increasing burden on chips. So whereas if you consider flexible electronics, which also known as flux circuits, it is a technology which is used for assembling electronic circuits by mounting electronic devices on flexible plastic substrates such as polyimide, transparent conductive polymer film. Also, we can use additionally these flex circuits. You can be screen printed silver circuits on polyesters. Here, the flexible electronic assemblies may be manufactured using identical components which are used for resin printed circuit boards and also allowing the board to conform to a desired shape or to flex during its use. And is there any alternative approach for this flexible electronics? Yes, we have an alternative approach to flexible electronics, which suggests various etching techniques to thin down the traditional silicon substrate to few tens of micrometers to gain reasonable flexibility. So which we just simply refer to as flexible silicon. That means it's almost approximately equals to 5 millimeters bending radius. You know, flexible electronics have recently attracted much attention since they enable many promising applications such as RFID tags, solar cells, biosensors, as well. If you come to the medical applications, electronic skin, e-skin, simply we can call it as, and e-paper, that is electronic paper, and flexible display. So if you cost, and they have lightweight, thinner, non-breakable, and new forms to create many new applications. Okay, so it is an attractive candidate for next generation consumer electronics, and they will soon be part of our daily lives. You have to accept this. And even if you consider development strategy of flexible electronics, which is depending on global technology progress and market forecast. Without market, whatever you are developing, it is waste. If you find some technology transfer and market forecast, then whatever, even you develop a small device, that also is going to play a vital role in the country. So currently it has been estimated that there are about 1500 worldwide research units who are working on various aspects of flexible electronics. And if you consider market analysis, which estimates the revenue of flexible electronics can reach it reached 30 billion US dollars in the year 2017, and we are expecting over 300 billion US dollars by 2028. Will you believe me? Right? So that is the beauty of the flexible or printed electronics. Right? So in this direction, let's see what are all the materials we are going to use for this flexible circuits. Right? So there are several materials, but we are considering base material, bonding adhesive, and metal foil. So in detail, let's go with one by one. So what is the importance of these flexible circuit materials? If you can go with, you may ask the question that you can go with, can't we go with any material? Yes. So it is 100% no, right? Because the function or performance of the flexible or printed electronic circuit depends on material. That is the first and foremost specification of this printed and flexible materials. So here, each element of the flex circuit construction must be able to consistently meet the demands which is going to be placed upon it for the life of the product. In addition, the material must work reliably in concert with the other elements of the flexible circuit construction to assure ease of manufacture and reliability. Right? So in this direction, we are considering different materials and what is the important role of each material. Let's see the brief description of each and every material for this flex circuit construction and their functions. So let's take the base material. So this base material is the flexible polymer film. It should be flexible polymer film. So which provides the foundation for the laminate. Right? So under normal circumstances, the flex circuit base material provides most primary physical and electrical properties of the flexible circuit. So if you go with the adhesive or adhesive less circuit construction, the base material is going to provide all the characteristic properties. Right? So wide range of thickness is possible with this, and most flexible films are provided in a narrow range of relatively thin dimension. You know, that dimension is also from 12 micrometers to 125 micrometers. But thinner and thicker materials are possible with this for this base material. If you go with the thinner materials, which are of course more flexible, and for most material stiffness increase, which is proportional to the cube of thickness. This is the beauty of base material. Then the second one, bonding adhesive. So here adhesives are used as the bonding medium, right? So for example, if you want to stick something, right? So we are going to use the Fevicol or Fevikwik. So that is adhesive material for bonding. So in the similar fashion, for this flexible or printed electronic circuits, we need bonding adhesive, right? So that is acting as a medium for creating a laminate. When it comes to temperature resistance, the adhesive is typically the performance limiting element of a laminate, especially when polyamide is the base material. If you change this base material, then this property is also going to be changed. So because of the earlier difficulties associated with the polyamide adhesives, many polyamide flex circuits presently we can employ adhesive systems of different polymer families. However, if you consider newer thermoplastic polyamide, which is also adhesive, which are making important for roads. As with the base fins, adhesives come in different thicknesses also. And the thickness selection is also very important, which is typically a function of the application. You just remember which should be a function of the application. We can take the example, different adhesive thicknesses is commonly used in the creation of cover layers in order to meet the fill demands of different copper foil thickness which may be encountered, right? And that is the medium which is acting as a medium between the flexible electronic circuit or printed electronic circuit. Come to the next material, which is metal foil. So the metal foil is most commonly used as the conductive element, right? So base material is going to provide the base for the flexible or printed electronic circuit. This is adhesive is going to provide the bonding, and metal foil which should have the property of conductivity, right? So here this metal foil is the material from which the circuit paths are normally etched. So you have wide variety of metal foils which are going to vary thicknesses, which are available from you can choose and create a flex circuit, right? However, you can consider copper foils, which serves the vast majority of all flexible circuit applications. And coppers maintain excellent balance of cost and physical and electrical performance attributes, which makes the circuit as excellent choice, right? So this is the importance before going to consider a circuit that is printed or flexible electronic circuit. You have to take that means you have to make sure that whatever the material you have chosen, which is suitable for your flexible or printed electronic circuit, right? So in this direction, let's consider what are all the different applications of flexible electronics, right? So if you take different applications of flexible electronics, you have a large number of applications which have been developed, including displays, computational systems, in energy storage and generation, as well healthcare and e-textiles. Like this, you just list out many more, right? So in this direction, first let's consider wireless networking, right? So that is our first application, and we have healthcare, automotive industry, smart textiles, displays, and human machine interactivity, electronic paper, right? So first let's consider wireless networking, how this flexible and printed electronic circuits are going to be used in this, right? So you just consider a stretchable antennas. I think many of you know about antennas. So here stretchable antennas which have been fabricated using poly dimethyl sileoxane, polydimethyl sileoxane. Simply we call it as PDMS. So which is usually cast on a photoresist mold with whatever the design you want. For that design, we are usually cast on a photoresist mold. And this PDMS structure is then peeled away and holes introduced for injection of a liquid eutectic. So which is going to form the radiating element. This is the beauty behind this stretchable antennas, right? So here you can also identify the research problem, that is a stretchable antenna. So you can introduce, because the substrate material you are going to peel off. After peeling off, we are just the holes are going to be introduced for injection of a liquid material. So why we are injecting the liquid? So because to form the radiating, it should act as a radiating element. So you can also consider another recently explored route for fabrication of this stretchable printed stretchable printed antennas, which are going to use direct deposition of thin film gold onto elastomeric substrate. So this is another recently developed or explored solution for this stretchable antennas. So in this direction, this printed or flexible electronic circuit is required, right? And if you come to the healthcare, this flexibility in electronic materials is very attractive for medical and bioengineering. Will you accept me? Right? So some electronics have been integrated into human bodies. For example, bionic eye, bionic ear, optic nerve, like this and so on. Heat, humidity, salt, or pressure sensor arrays can be used as bed sheet and monitor a patient in real time. That is the beauty of this printed or flexible electronics circuits. So flexible thin films could also play a key role in deciphering the thought process occurring in the brains. That is also another research area, right? So like this, these circuits are going to play a vital role. And other one is automotive industry. So we have intelligent roads, which will be engineered with the aim of improving road safety and lowering the road congestion. Also, we can go with the energy consumption. So in this direction, the road and vehicle will also be able to interact dynamically by adjusting either party to energetically optimize their systems. So like this, printed or flexible electronics are playing a vital role. Then smart textiles. recently, if you consider, there is an increase of interest in smart textiles for health monitoring, entertainment, and display applications. So these smart textiles can be embedded with multiple sensors and display devices for monitoring stress, toxic gases which are present in environment. And each smart thread is basically a shift register with a small display pixel and possibly a sensor, which can be used to transfer data from one end to other end, right? And if you come to the next application, which is nothing but displays and human machine interactivity. As a user slide fingers on the surface. So now apply the time varying potential, which includes intermittent attractive and repulsive electrostatic forces between the buried conducting layer and the finger, right? So this electrostatic attraction varies the normal contact forces between the user's skin and surface, and in turn, which is going to modulate the dynamic friction and touch perception, right? And come to the electronic paper. So currently, the most successful technology and industry is electronic paper. The main applications are e-readers, electronic shelf labels, smart cards, electronic posters, and so on, right? So currently, the e-reader is not really flexible because it uses a glass backplane and e-ink holdings, which includes organic conductor and printing process. And the substrate is not with, that means using different films, which only can be processed at lower temperatures. And it also develops a passive technology of cholesterol liquid crystal, which can be manufactured using a fully roll-to-roll technology. This is another area of research, roll-to-roll technology, right? So in this way, you keep on apply this printed and the flexible electronic circuits in various applications, right? And at the same time, any device or anything, it has their own advantages and their own limitations. So here, if you go with advantages, which has lightweight, and the dimension of this is very, very small. And if the size is very compact, then you can also save the space. And this printed or flexible electronics is you can fold and bend. This is simply we can say that foldable and bendable, and it increases the circuit density. And you can view these type of circuits in from any angle. So that means a wide viewing angle. And at the same time, you have several limitations also, right? So those limitations are initial investment is going to be very, very expensive. And also because of the smaller size and or we can say that compact in size, the integration of components is very challenge for the engineers. And the requirement of machinery is very precious. And here lifetime is very small. It is not having a long lifetime. And because of all these, the manufacturing is also going to be difficult, complex. So finally, I'll go with the challenges of this printed or flexible electronics, and I'll wind off. I will hand over to Dr. Mariappan. So here, if you, after hearing all this, what are all the challenges that still need some improvement, right? So here, if you observe these type of things, here electrical instability This is the first challenge, electrical instability. So really here, the reliability is critical for flexible circuit design, and you have to ensure that the circuit would operate reliably throughout its lifetime. But as we saw that in the limitation, we have lifetime is one of the limitation. So thin film transistor, if you consider TFTs, often which are going to suffer from electrical instability, but threshold voltage shift of a single thin film transistor can be modeled by analyzing its operating conditions, and circuit lifetime can be predicted accordingly using SPICE simulation. That is the beauty, right? And the second challenge you can consider printing quality. That is also, we saw that one of the limitation, printing quality. So the printing qualities are not easy to control due to liquid offset or jetting operations, special multi-layer or large area film printing, right? And other challenging is flexibility operation. So the most practiced flexible operations like bending, folding, or rolling is not easy guarantee due to multi-layer structure. And research is going on this to provide more reliable flexibility to that circuits, to those circuits. Okay, so then come to the next challenge, flexible substrate handling and alignment. So the dimensional control of plastic substrate is very difficult due to temperature, humidity, and tension variation, and special roll-to-roll operation also. Okay, and finally, we have the challenge on flexible conductor conductivity and work function. If you consider this here, the operation for flexibility and conductivity or the trade-off parameters we can consider, and work function always needs to modify, right? So these are the challenges we have to take care when you are going to design the flexible or printed circuit for various applications, right? So this is the very small introduction about the printed and flexible electronic circuits. I think Mayappan sir will elaborate the things related to this flexible and printed electronic circuits. Thank you.
Ma'am, thank you so much, ma'am. You have given very nice intro and in the detail of applications even. I'm very thankful for that. Before going for sharing this video, I'm just giving introduction about our resource person, Dr. Mayappan, M. Mayappan, Mayappan otherwise, is Chief Scientist for Exploration Technology at the Center for Nanotechnology, NASA, Ames Research Center in Moorefield Field, California. Until June 2006, he served as a director of the Center for Nanotechnology. He is a founder member of Intra-Agency Working Group on the Nanotechnology, established by the Office of Science and Technology Policy. The IWGN is responsible for putting together the National Nanotechnology Initiative. Dr. Mayappan has authored or co-authored over 200 articles in peer-reviewed journals and made over 200 invited keynote plenary talks in nanotechnology subjects across the world. His research interests include carbon nanotubes and various inorganic nanowires, their growth and characterization, and application development in chemical and biosensors, instrumentations, electronics, and optoelectronics. Dr. Mayappan is a fellow of the Institute of Electrical and Electronics Engineer, the Electrochemical Society, the American Vacuum Society, the Materials Research Society, Institute of Physics, the American Institute of Chemical Engineers, and the California Council of Science and Technology. In addition, he is a member of American Society of Mechanical Engineers. He is currently the IEEE Nanotechnology Council Distinguished Lecturer on Nanotechnology, IEEE Electron Devices Society. Distinguished lecturer and was ASME's Distinguished Lecturer on Nanotechnology from 2004 to 2006. He served as the President of IEEE's Nanotechnology Council in 2006 to 2007. He currently serves as the Vice President of IEEE Areas for Educational Activities. For his contributions and leaderships in nanotechnology, he was received numerous awards, including the Presidential Meritorious Award, NASA's Outstanding Leadership Medal, Arthur Fleming Award given by Arthur Fleming Foundation and the George Washington University, IEEE Judith Reshnik Award, IEEE USC Harry Diamond Award, and so on. So I would like to share his video. He's unable to participate because of the timing. So I would like to share his video. I'm happy to have this lecture. Sir, Madhu sir,
Ma'am, yes, ma'am.
shall I continue?
I think there is no audio from your end, ma'am. So I have downloaded it. If you allow me, I'll share it. You stop sharing.
Yes, please. Sir.
You stop. Yes, ma'am. I'll share, ma'am.
Yeah, I have stopped. I have stopped.
Yes, ma'am.
Okay, I stopped, sir.
I'll do it from my end. 1 second, ma'am. I'll share it. Just 1 second.
Hello, everyone. Thanks for joining me today. I apologize.
Madhu sir,
Ma'am, I'm sharing, ma'am. Once.
only voice is coming. No.
Yes, ma'am. Now just give me feedback.
Okay, sure.
Is it okay, ma'am? Can you see the screen?
No, sir,
No.
not yet.
Yeah.
Can I go, ma'am?
Yeah.
You can double click so that entire video, entire screen. Now it is seen.
Make this presentation live so that I see what we can do. Hello, everyone. Thanks for joining me today. I apologize. I'm not able to make this presentation live so that I see what we can do. Given these circumstances. The talk about my talk today is printed and flexible electronics. I'm going to focus on energy and environment related applications. So why printed electronics to begin with? I'm sure you all heard about this Internet of Things. People are talking about multi-billion-dollar economy emerging out of this IoT in the coming decade. The components that are needed for this IoT were flexible and they necessarily have to be very inexpensive. We can very well afford to make them in clean rooms and fabs and then deliver them from your house. The possibility is that you may have to make them on demand. And so additive manufacturing has been around for a while and way backward. That's essentially 3D printing, mostly both materials and graphic components. So printed electronics, you can think of it as the substrate of additive manufacturing, but it's mostly 3D printing, primarily on substrates. So these are all going to be critical technologies of the future. So what is going on today with printed electronics is mostly early stage research activities, primarily at universities and some dedicated institutes, pretty much all across the globe. And small and big companies are engaged in this activity in the U.S. and in many other countries. In the U.S., there is a consortium called NextFlex, and that is aiming to create a U.S.-based ecosystem to manufacture these printed electronics devices. So there was a reason why I took printed electronics as a topic for my talk today. It is not a secret that India missed the last electronic revolution. So in the IT domain, India's major contribution is software. My question is, can you afford to miss the next revolution? If you miss it, then you will keep importing hardware over and over again. That is going to be difficult, and particularly a country as fast, the size of India, cannot afford versus Europe. I think a massive country like this, you need to participate in all the activities. And in this particular case, you don't need billion-dollar fab, like in the case of the silicon integrated circuit manufacturing. So in that sense, system electronics is going to be critical for the Indian economy, for job creation, and for trade and other. There is a center on flexible electronics at IIT Kanpur. It is a world-class institute with top-notch facilities. It is in the top 1 or 2 in the world, if not the first in the world. So, and they are open for collaboration. I'm fully aware of the activities that are going on at IIT Kanpur, projects. So moving along, if you take a look at the literature, you will see a lot of papers on a variety of applications, graph improvement, simple, simple practices, memory development, welding, and planners are most investigated by simple electronics, for energy storage, super traveler, and batteries. I have even seen people, putting solar panels. So these are all a variety of components, that have been printed in the literature. I'm going to focus on only two things there. The one is gas sensors for the environment, and then the supercapacitor at the energy storage device. So before we go into applications, I want to spend a little bit of time talking about, materials and the practical. So the first one is, what are the flexible substrates? Obviously, the most popular ones are various polymers and plastics because they're very well developed and they're very readily available. And the properties are very well known, and the methods and practicing techniques, everything is very well known about polymers and plastics. The two other flexible substrates, one is paper. Paper is pretty expensive and it's a very green technology and biodegradable. It's ideal for one-time use, biosensors for healthcare is a one-time use. There is a possibility to engage roll-to-roll printing, to make it fairly inexpensive. And cotton and other types of textiles, they're ideal for wearable technology. So this slide shows what is possible down the road. Okay, so this is more or less like a vision, integration of many different components on a flexible substrate. For example, you can have an RF antenna, and you can have some biosensors or gas sensors, and thin film circuits. To run all of these things, you need power, so you can have a printed solar cell providing the power. Anytime when you generate power, you may not be able to use it right away, so that means you have to store it. So you can store it in a battery or supercapacitor. So this is a vision of integrating many different components on a single big flexible substrate. We are not ready there yet. It's not possible today. A lot of different groups are working on individual components, but it's going to take time to put all these things together, and probably in a decade or so, we'll see. So now, moving along, the printing process. The most common printer is inkjet printing, which is no different from the desktop printers that we use, except the materials that we print are very unique. They could be metallic inks, semiconducting inks, and dielectric inks, and so on and so forth. There are a bunch of different platforms, a bunch of different companies selling units which are ideal only for research purposes, or then some companies have fairly large units which are very useful for manufacturing. One of the key things in printing technology like this is, once you're done printing, it's not quite ready for application right away. You would probably need to do some kind of an annealing or sintering process, which could run anywhere from 100 degrees to 250 degrees centigrade. So after that, you can get a consolidated thin film, which is ready for fabricating your sensor or electronics or whatever. There is a downside to that because that kind of a high temperature processing, may not be ideal for, for delicate substrates. If you happen to be printing on silk or cotton, 250 degrees centigrade may not be ideal. So those are some of the constraints that you have, with current inkjet printing and other kind of printing processes like aerosol printing. So there is an alternative which I just want to bring to your attention. This is called atmospheric pressure plasma jet. It's an alternative to inkjet and aerosol printing, and this was developed by a guy by name Ram Prasad Gandhiraman, who's from Chennai, and he worked with me for a number of years. And after successfully developing this in my group, he licensed patent from NASA and started this company, and the company is called Space Foundry. You can Google it to get more information. But what this involves is, instead of using an inkjet printing cartridge, what it is the same ink dispersion. Basically, a helium carrier gas can bubble through that, and it can pick it up, and then go to a glass tube. So this is the image on the top is an experimental device that was developed in our lab. It was a glass tube which is only half a centimeter diameter. And there are two copper tapes, wound 2 centimeters apart, and they serve as two electrodes. One electrode is grounded, the other electrode has got a DC power supply. And this creates a dielectric barrier discharge, so it's an atmospheric pressure plasma. And you can use helium or argon or nitrogen, any of those inert gases, to bubble through the ink and pick up the ink and then go to the plasma. So now what it is this plasma jet can shoot across onto a substrate. The substrate may be paper or textile or the polymer that I talked about earlier on. And you do the deposition, from the nozzle. And what you have here that is coming out of the nozzle and gets deposited on the substrate, that gives consolidated thin film right away. Okay, so in that sense, it is a single-step process. You do not need to do the sintering or annealing step that I talked about, which is the downside of the inkjet printing. Here, basically, it takes care of consolidating the thin film. So this is an in situ single-step process. So the image on the bottom is a commercial version of the plasma printer from the company called Space Foundry. This is Ram's company. Just to give some examples of the plasma deposition. This image shows multi-layer carbon nanotubes deposited on paper. The image on the left is basically carbon nanotubes deposited with the plasma off. What you see here is nanotubes here and there, and the density is kind of low. The connectivity is kind of poor, and if you measure the conductivity is not all that great. On the other hand, the image on the right is you turn the plasma on. Now you see a much higher density of carbon nanotubes. The interconnectivity of all these carbon nanotubes is very good. And also, when you measure the conductivity, it's a value that you normally expect, for a thick film of multi-layer carbon nanotubes. So that tells you plasma is doing something. Okay? So the next slide shows silver nanowires deposited on cotton. The top images, SEM images, they show different magnification. You can see very highly dense silver nanowires on cotton. Anytime when you deposit things on cotton, cotton obviously it's got to be flexible. So the conductivity takes a little while, to stabilize. So you do about 20 or 30 printing cycles to begin with. During that initial process, the conductivity keeps changing, and then after about 30 cycles or so, it stabilizes. So it takes a while to stabilize and then give a constant conductivity. Now, once you get the constant conductivity, then the value stays pretty good, for many cycles and for a long time. So the next slide shows silver nanowires deposited on a 3D printed object. Okay? So most of the printing, like inkjet printing, you can do it on 2D surfaces only. You cannot do inkjet printing on a 3D object. Whereas this plasma printer, the nozzle, you can scroll the nozzle over a 3D printed object. So the left-hand image at the top, it shows a small bird. It's an owl. It's a plastic bird, which was 3D printed bird. As you know, plastic doesn't conduct. So then you can use the plasma tool to deposit the silver nanowires all around the bird in a conformal manner. Okay. So now you can connect a battery on one side and then connect the LED light on the other side. You can see the LED lights up because the silver nanowire conformal coating on the bird makes a plastic bird completely conducting. So in that sense, this plasma deposition tool is a versatile tool. It not only can print things on paper and cotton and plastic substrates, but it also can print on 3D objects. Okay? So moving along, and now I want to start focusing on applications. And the first application that I want to talk about is gas sensors. And gas sensors are ideal, are necessary for monitoring outdoor air quality, pollution, things. And people are talking about smart homes and air quality monitoring. So the gas sensors have a variety of other uses, as you can see in the slide. So what I'm showing here is ammonia sensing results, from this, plasma printed carbon nanotubes. They say the production limit of this is about 1 part per million, which is as good as actually silicon-based sensors we used to make about 10 or 15 years ago. So the fact that actually you're printing devices, that doesn't make the sensitivity of the detection limit any worse than what it used to be on microfabricated devices. But the way the gas sensors work is, the material like carbon nanotube or graphene, upon absorption of a gas or a vapor, the resistance can change either increase or decrease, depending on the polarity of the gas. Okay, so your output signal is only resistance, but how do you actually convert that output signal into a concentration? Okay, so to do that, we need to construct what is called the electronic nose. Okay, so if you think of a mammalian nose, like a human being or a dog, we have thousands of cells in our nose, and but not each cell can smell every compound on Earth. Okay, so what it is also we don't have dedicated cells, let's say for chutney, or for chicken, or for strawberry or mango. We don't have cells dedicated for different things. Some cells will respond to a particular order, and then a single order actually can get response from multiple cells. So in that sense, it is like a matrix-like operation. And so what it is right from the beginning of our childhood, every time we learn about a new smell, the name for associated name for that actually gets registered in our brain. And then over a period of time in our lifetime, we accumulate the smell name combinations in our brain. And then every time when we smell something, basically we dial back in our brain and then we recognize the smell. So we have to create this in the electronic nose, okay? And for that, you need, pattern recognition algorithm. So here I'm showing an example of actually only 2 compounds, carbon dioxide and ammonia. We use 8 different sensors in the sensor array chip. They're all carboxylic acid functionalized carbon nanotubes, but each with a different pH. And so we use artificial neural network, to convert the measured, resistances into concentrations. So the images on the top, convince you that the trained model predicts the gas type and the concentration accurately. So even though I'm only showing here two gases, you can add other, polluting gases like carbon monoxide, methane, and ozone, and sulfur dioxide, and any number of things, and then you can expand the artificial neural network, to train and predict the gas type and the concentrations, accurately. So this is just a simple example, and the details are given in this ACS Applied Nanomaterials paper, which you can take a look at later. Moving along, and a couple more examples. Printed biosensors, they are useful for water quality monitoring, and then again, monitoring other kind of pollutions in the environment. Okay. So this is an inkjet printed biosensor. So this basically has a working electrode, which is made of carbon nanotubes, and a counter electrode, which is also made of carbon nanotubes, a reference electrode, which is silver chloride electrode, and then we use protective dielectric, which is a polymer film. So the bottom image you see is the printed three electrodes. So you can get the size of those electrodes. It's a US 25-cent coin, so that can tell you, what the real size of it is. Okay. So I was hoping to show you some E. coli, results, but I don't have it at this moment. So I'm showing you here electrochemical response of a cardiac reactive protein. Cardiac reactive protein is an important biomarker for heart attack, and so we attached an antibody for this cardiac reactive protein, and then when the antigens, from the target blood, when they bind, actually, the signal changes. So the blue is without the CRP, and the red is actually with the CRP, and we are able to detect as low as 75 nanogram per ml of cardiac reactive protein. So this is a fairly good number for printed electronics, and we hope to improve this all the way down to 1 nanogram per ml, in the coming years. So the last example that I want to talk about is energy storage, and I'm using supercapacitor as an example. The supercapacitor we have fabricated is an end-to-end printed. Okay, we even printed the substrate, and the substrate was printed by an FDM method, and the base substrate is ABS, and then we use polyvinyl alcohol as a planarization layer, and then we fabricated a current collector by directly printing silver nanoparticles. So we fabricated two common types of supercapacitors. One is the electrochemical double layer capacitor. The other one is a pseudocapacitor. The pseudocapacitor works, somewhat like a battery because it has got, redox reactions. So the EDLC essentially consisted of activated carbon. It gives very large surface area, whereas a pseudocapacitor, the active layer is graphene and manganese oxide nanocomposite. That is needed for effective surface redox reactions. And we used a gel polymer electrolyte, and you can see the electrodes, interdigitated electrodes that we printed on the top right-hand side. These are the cycloalternative results of both the EDLC and the PC. So you can see the hysteresis loop. What they mean is that actually these devices work as the energy storage devices, as you would expect. So the last slide I want to show on the printed supercapacitor is we check the lifetime in charge discharge cycle of these devices. It has worked 1,000 cycles in rubber, and it can potentially work about 500,000 cycles. The pseudocapacitor works only about 40,000 cycles because it has got redox reactions like battery. So obviously you can't expect that to work that many cycles, but still 40,000 cycles are really amazing. The specific capacitance of these printed supercapacitors are about 170 farads per gram, which is a pretty good number. the energy density is 15 watt-hour per kg, and the power density is 2 kilowatts, 2 kilowatts per kg. So these are all, very good numbers. So that brings to my concluding slide. So essentially, the printed electronics is a rapidly evolving area. It allows you to prototype all sorts of components and parts. But today, I gave you a couple of examples of, gas sensors for air quality monitoring, and biosensors, potentially for water quality monitoring. The printed supercapacitors, with very good, performance. So potentially, there are many, many applications that printed electronics can cover. With that, I will end the talk. If you have any questions, you are welcome to contact me by email at your convenience. Thank you.
Thank you very much, Madhukumar sir. We have heard very fantastic contribution and presentation by Dr. M. Mayappan, Chief Scientist for Exploration Technology, NASA.
At your convenience. Thank you.
At this
Cover. With that, I will end the talk. If you have any questions, you are welcome to contact me by email at your convenience. Thank you.
Thank you, Madhukumar sir, for sharing. And we are very grateful to Dr. Mayappan sir,
End the talk.
Chief Scientist, for his contribution and presentation to this webinar. I would like to thank the management and staff of our institution, Sri Vidyaniketan Engineering College, for their support and for conducting the webinar. I would like to thank our HOD sir, Dr. P.V. Ramana, for his continuous support for conducting this webinar. I would like to thank Dr. B. R. Anita ma'am for entire support of this webinar. I am thanking with heart to Mr. M. Madhukumar sir. Without him, this would not be possible.
Thank you, ma'am.
Finally, I would like to thank all the participants for your patience of learning and hearing. If you are requesting, I can share the records and you will receive your participation certificate today or tomorrow. Thank you all. Let us continue for the above next webinar then. Thank you so much.
Ma'am, I'll end the stream.
Okay, sir.
Yes, sir.
Thank you all.
Thank you. Thank you.
Thank you. Thank you, ma'am.
Thank you, ma'am.